Hey everyone! This is Gayatri from Youthbuddy. Dear students and aspiring programmers interested in assembly language tuning in. A structured roadmap can help you understand how computers work at a deeper level. Here's something helpful for you, a deep study roadmap for assembly programming language from Youthbuddy. Assembly language is a low-level programming language that provides direct interaction with computer hardware. Unlike high-level languages, assembly is closely connected to machine code and processor architecture, making it valuable for understanding how computers operate internally. The journey begins with learning computer architecture fundamentals. Students should understand the CPU, memory, registers, instruction cycles, and how different hardware components work together during program execution. A strong understanding of binary and hexadecimal number systems is also essential. Topics such as signed and unsigned numbers, binary arithmetic, and 2's complement form the foundation for assembly programming. Learners should then explore the relationship between machine code and assembly language. Understanding how assembly instructions translate into binary operations helps build a deeper understanding of low-level computing. Students should also become familiar with assemblers and development tools used to write and test assembly programs. Once the basics are established, the next step is learning core assembly programming concepts. Important topics include registers, data movement instructions, arithmetic operations, logical operations, and control flow instructions. Understanding instructions such as MOV, add, sub, JMP, call, and ret helps learners create functional assembly programs. Working with stacks, procedures, and function calls is another important milestone. These concepts help students understand how programs manage memory and execute tasks internally. Memory management plays a central role in assembly programming. Topics such as addressing modes, pointers, offsets, segmented memory models, interrupts, and system calls provide insight into how software interacts with hardware. As skills grow, learners can move into advanced concepts. Topics such as macros, directives, bitwise operations, string manipulation, floating point instructions, and performance optimization help develop more efficient programming techniques. Modern assembly development also includes understanding protected mode, real mode, 64-bit architectures, and how low-level code can work alongside languages such as C and C++. Practical projects are essential for building confidence. Simple utilities, string processing programs, calculators, and bootloader experiments can help transform theoretical knowledge into practical skills. Assembly knowledge is particularly valuable in areas such as embedded systems, operating systems, cybersecurity, reverse engineering, firmware development, and performance optimization. By mastering computer architecture, memory management, instruction sets, and practical low-level programming techniques, students can develop a strong foundation for advanced computing fields. Stay tuned for more useful info. For more details, click the link in description or explore it directly in the education section on the Youthbuddy website. Like, share, subscribe, and follow our social media accounts for more updates. Yours Gayatri from Youthbuddy, signing off.